Hi everyone and welcome to today's Physics Daily Booster. This is number 18 in our series, and what we're doing today is only for those of you doing GCSE Physics higher tier. If you're doing GCSE Physics Foundation or combined, then nothing here is relevant to you, full stop. What we're going to start off with then is the idea of electromagnetic induction. So, what is electromagnetic induction? Well, if you move a wire in a magnetic field so that it's actually cutting the field lines, what's going to happen is we're going to induce a potential difference across that bit of wire. Now, that's not the only way we can do this. We can also achieve that by making the magnetic field change around the conductor. But the key thing is the field lines are being cut, because if the wire doesn't cut those field lines, we will not induce a potential difference in the wire itself. So in order to actually have this whole idea of electromagnetic induction, a wire must cut magnetic field lines. That's kind of like the first principle, if you like. In terms of how we can increase this induced potential difference, then we're trying to cut more field lines in a given time frame, basically. So one way we can do that, move the wire faster, because if you move it faster, it's going to cut more field lines. We can use a stronger magnetic field, because remember, stronger magnetic fields have more field lines within a given area. Or we can use more wire or more coils on some wire, because again, we're just going to cut more field lines in that same time frame. All of those are going to increase that induced potential difference in the wire itself. Why do we do this? Well, if we actually connect that wire into a circuit, then we've got a complete circuit and therefore current is going to flow, because we've got potential difference that we're inducing and therefore current will flow. When current flows in a conductor, then magnetic field will be produced. So what we find here is if that wire is in a magnetic field, then a force is going to act on it. What we find in terms of the magnetic field being produced, it's in the opposite direction to the field that produces the potential difference in the wire. So what we're really seeing here is that we're getting the ability to create some form of movement through the fact that as that current flows through our conductor, we're generating a magnetic field. That magnetic field interacts with the pre-existing one, and therefore a force is going to act on the wire itself. This is probably the little demonstration that you saw in class. Metal tube, drop in a magnet through it. The reason that this works then, and the reason the magnet falls really nice and gently through that tube, is the magnet has its own magnetic field, obviously. As it falls through the tube, what it's doing is it's inducing a current in the pipe. Because what we're doing is as the magnet is moving, obviously the field lines are being cut by the actual metal of the pipe. Because it's a circular loop of basic metal, then what we find there is we've induced a potential difference and therefore current is going to flow. Because we've now got a current flowing in our little pipe, then we're going to produce a magnetic field from it. The direction of that magnetic field is going to end up repelling the magnet, because it's in the opposite direction to the one of the magnet. So what we end up with is basically a magnetic field that repels the magnet, and therefore it falls slower through that metal tube. All going back to our idea of this induced potential difference. So the magnet induces a potential difference in the pipe. That allows the current to flow. Because we've got a current, that produces a magnetic field of its own. The magnetic field produced by our pipe is going to be in the opposite direction to that produced by the magnet. They repel each other and therefore it falls more slowly. So how do we use this then? Well, we've got two different devices we're going to look at. We're going to look at alternators and dynamos. In an alternator, then our coil of wire is going to be spinning between the poles of a magnet. As a result of that, because we're actually spinning a coil of wire in between the two poles of a magnet, we're going to generate that alternating potential difference, and The reason that we do that is we're cutting field lines. It's alternating because the potential difference is changing direction. So if we were to plot a little graph showing what's happening, we get this. So you can see current is going to be going into positive and negative regions. And what we can see following that little line, it goes into the positive region, that's our maximum forward current, and then it's going to come back down to maximum reverse current when we are, obviously if you look at the little coil positions at the bottom, so you start off with a vertical positioning if you like, when we're dead on our zero line. As we go 90 degrees, we hit our maximum forward current, another 90 degrees, we're back at our zero line, another 90 degrees, maximum reverse current, and then back to the start position on the zero line again. So what we see there is that one complete turn gives us a positive and a negative. So we've got an alternating potential difference. The way that we set up this device then is we use these things called slip rings. So if you look at the little diagram on the right, you can see we have these two little metal rings, and basically nestled against those are carbon brushes. So they're not physically attached to them, they literally just rest against it. So that what happens is, as it's turning, the carbon brushes are always in contact with those slip rings, but they're not physically attached to them. And that's important because it avoids the coil from tangling. If you'd attach the carbon brushes permanently onto the slip rings, then all that would happen is you just twist it up into a tight, basically knot, it wouldn't work. So they literally just allow it to brush through but always keep contact. Second option, the dynamo, this is going to create a direct current. Now what we find is in a direct current, it will always be the same direction because the potential difference we create is always going in that same direction. This one, to achieve that, uses a split ring commutator. So what we've got, two different types of rings involved here. In our alternator, it is the slip ring, and in the dynamo, split ring commutator. What we find then, here's our little diagram of what's actually happening down in the bottom left here. We can see we've got our split ring commutator, so the one with the gaps between the two halves, remember. We've got the carbon brushes there that rest against those split rings, and then we've got our coil of wire within our magnetic field. So what's going to happen is, as it rotates, obviously as the little gaps come level with the carbon brushes, it loses contact for that very brief moment. Momentum is still going to allow it to carry on, and then when it reattaches, all it means is we end up with potential difference that is only in, say, the positive region here. Nothing in the negative, because all we're doing is disconnecting and then reconnecting on the other side. So what we find, the direction of potential difference does not change, but the magnitude does, as you can see from the fact it is a curved line there. In terms of how we could increase the output of either an alternator or a dynamo, same things apply. We can use a stronger magnetic field, use more turns on the coil, or spin the coil faster. So any of those three will increase the output of an alternator or a dynamo, whichever one you happen to have. Obviously, if there are bits you'd like to look at in more detail, there are the main videos on the channel under the P4 playlist. You can also use your revision guide, have a look at some past exam papers to get a bit of a feel for the style of questions that come up here. And then, of course, don't forget to join us again tomorrow for the next Physics Daily Booster.